All right, guys, welcome to section C of chapter 4. We're going to continue talking about the periodic trends on the periodic table. So last section, we talked about those energy levels. The electrons orbit around the nucleus at different orbital places. And that coincides with the periods on the periodic table. So the elements in the same period have the same number of electron levels. So for period 1, oh boy, I gotta get my pen here. There we go. So for period 1 up there in the red, that's 1 energy level. Period 2 has 2, 3 has 3, 4 has 4, and so on. So every time we go down a row on the periodic table, we're adding a new orbit for those electrons. And then the elements within the same family, remember that's these vertical columns, have the same number of valence electrons, and those valence electrons are those outer electrons. The very inner level, so for this top period, there's only a spot for 2 electrons there. These models down here, both of these are called Bohr models. And what they show is in the center, they show how many protons and neutrons there are for each of those elements. And then the rings coincide with those energy levels. And you can see the inside ring on both of them only have those 2 electrons. And then as we move out, typically it can carry 8 electrons. So for proton number 8, remember the proton number coincides with the atomic number, so that would be element number 8. So this is actually oxygen right here. Oxygen, okay? 2 of its 8 electrons are on that inner shell, and then there's 6 on the outer shell. And oxygen would be in this family right here. Let's see, for the number 20, protons of 20, that is element number 20, which is calcium. And you can see that we're up to 4 electron rings now, and calcium is in fact in period 4. Calcium would be down here. Specifically this spot, okay? So the fact that it's in the 4th period tells us it has 4 electron rings. The fact that it's in this second family tells us that it has 2 valence electrons. And you can see that it does in fact have 2 electrons on that outer ring, okay? So that's kind of one of the biggest patterns we see within the periodic table. Just based on the location of the element itself, we can tell a lot about the electrons and the number of protons. Okay. There's another way that we can show this. This method called the electron dot notation, also known as the Lewis dot structure. The dots are just written right around the symbol of the element. Okay. And those dots represent the valence electrons. And there's a maximum number of 8 valence electrons in the outer shell. And so just by showing these dots, you're showing how many valence electrons they have. Group 1 has 1, group 2 has 2, group 17 has 7, group 18 has 8, and so on, and you can just kind of count the rest there, okay? So as we move down a group, the number of valence electrons is the same. It's the energy level that increases. So that outer electron is in a farther orbit, but the number of outer electrons, those valence electrons, is the same, and that's why we get those similar properties. So all of these in group 1 have 1 valence electron, which makes them very reactive. As we move left to right, not taking these transition metals into account, we add 1 valence electron at a time. Okay, so from group 1 and 2, and then 13 through 18, we're gradually adding 1 at a time until we get to these noble gases on the end, which are full. Helium is also considered non-reactive because it only has the 1 ring that can only hold 2, so it's also considered full and therefore pretty stable. All right, so because of this, we get some periodic trends, okay? We get some patterns that we see as we move through this periodic table. The book talks about 2 of them. We talk about the atomic radius, which is basically just the distance from the nucleus to the electrons itself, okay? And so the bigger the distance, the greater the radius. And we increase as we move down and over to the left, okay? Sorry, this is backwards. I fixed that because I was thinking it was a typo. It's not. So we increase the atomic radius as we go down, but it increases right to left or decreases left to right. Oh, I did have that right. And I got to learn how to read. Anyway, the other one that the book talks about is electronegativity. And that electronegativity, you can see that here and here, is the element's ability to hang on to its electrons. And it is related to the radius, okay? So the smaller radius means those electrons are closer to the center, which means it can hang on to them easier. So the smaller the radius, the greater the electronegativity, and then vice versa, okay? So we see that kind of moving in an opposite direction of that atomic radius. Electron affinity just means it's very similar to that electronegativity. It's how tightly they hang on to those electrons. Ionization energy is the energy needed for an element to actually give up an electron. Okay, and so the higher the energy, that goes in the same direction as the electronegativity. So the higher the electronegativity, the tighter it's hanging onto the electron. So the more ionization energy is needed. So both of those travel in the same direction. And then we just get some general metallic and non-metallic characteristics, whether it's conductivity or the shininess or the malleability. We have more metallic characteristics here, and then the more non-metallic characteristics up there, okay? So just some general trends, not quite as helpful as talking about the energy levels or the number of valence electrons, but definitely some trends that we see there. Okay, here's just a couple of more Bohr models and those dot structures. These are both sodium, and these are both iodine. So if you look up element number 11 on your periodic table, that is sodium. You can see that sodium is in the third period because it has these 3 orbits, and it has 1 valence electron, which is represented with that 1 dot there, okay? Iodine is element number 53. Iodine is in period 5 with those 5 layers there. And iodine actually is in that family number 17, which tells us it has 7 valence electrons. And that's why there's a dot missing right there. Now, these two elements are very strongly attracted to each other. Elements that have 1 valence electron really like to react with elements that have 7 valence electrons, because that magic number 8, 1 plus 7 is 8. And there's different type of bonds that can happen as a result of this, which we'll talk about later. But ultimately, these two could come together and share those valence electrons. And whether that means that extra one is literally flying around both of these elements, or it means that that electron from sodium physically moves over to the iodine, it depends on the kind of chemical bond we're talking about. And we'll talk about that more later. All right? That's all I've got for you guys today. See you later.